This is like kind of the last session, and everybody has kind of Java'd out. You know what they say is a lot of Java code, a lot of coding, a lot of architecture, a lot of technical discussions at the end of the session. So so I will try to make this as interesting as possible. So, but let's make this very interactive because it's a small group. I'd like to let's be the audience 2.0. So if you have any questions, interrupt me rather than talking about at the end of the questions. Today, so I'm Jinesh Varia. I'm the technology evangelist on the Amazon Web Services team based in Seattle, Washington, and focus mainly on the infrastructure offerings of Amazon. Infrastructure, so how many of you were already present in the cloud computing session before? Okay, sweet, very cool. So I'm not, so based on the information from the organizers, they gave us some input about cover a little bit of overview. So that was my previous session, an overview, a very high level overview of what people are doing with cloud computing and how is it being used, how are other applications being built, what are people building on it and stuff like that. That was on the earlier session. In this session, we are basically going to see the power of cloud computing, and I will share with you an architecture that we have built, which is massively scalable in all dimensions. And I'm going to introduce a term called cloud architectures, which basically will explain, which will talk about this particular example of the architecture. So any questions, anything that you have, just feel free to interrupt me, raise the hand, and let's just have a conversation. So, basically, I assume that most of...
Excuse me, sir.
Sure.
I'm sorry to interrupt, but can I ask the people in the front, please? Because few people...
So I assume everybody is... how many people have an account at Amazon Web Services? Okay, 5, 6. Okay, cool. So Amazon Web Services is the infrastructure or the technology arm of Amazon.com. We are basically focusing on providing highly reliable, rock-solid infrastructure on an on-demand fashion, providing with on a simple web services interface. So I kind of had an overview in the last session. In this, I will touch a little bit, but I want to focus more on the architecture itself that we have built that uses all the services that we talked about in the previous session. So I'm going to talk about and of course it's built in Java and it scales in Java, so it's Java-based cloud architecture. And I'm going to talk about Hadoop. How many people know about Hadoop? Okay, few, cool. So okay, Hadoop is open source distributed processing framework. It is a way by which you can do massively parallel jobs across multiple nodes, and then aggregate the results back into your results, into your application. So I'm going to talk about that. It's based on Google's MapReduce algorithm. And I'll talk about how we are using this in our internal systems. At the end, I will talk. There was a question in the earlier session about what are the problems that we faced when we to scale, and these are problems that everybody faces when they are when they are trying to solve the scalability problem. So I'm going to talk about that and talk about in general how we scaled and share some of the best practices and other aspects. So let's get started. These are Amazon Web Services, as you might know. I'm going to focus mainly on the infrastructure as a service. There are Amazon Simple Storage Service, Elastic Compute Cloud, SimpleDB, which is database in the cloud, and the Amazon SQS, which is a queuing mechanism that that you can use as a buffer between the two applications. So there are other web services in the buffet, but if you and we encourage people to pick and choose the services that they feel are important for their application and make the whole meal out of that. This is a paper that I'm writing up a research paper to submit for a conference for IEEE, and this where I'm talking about the concept of cloud architectures and the aspect about how we can build effective service-oriented architecture. I'm going to skip all this section because everybody knows about this. So let's start with the use case. It's very, very important to start with the use case. Think about any application that takes a lot of time to compute, that takes a lot of time to process, that needs a lot of computation power as well as it's data intensive in your part of the business. So in any business, any application, say if you are a pharmaceutical company, you would want to know want to locate the people who were given out a particular drug, perhaps an unsafe drug, and you want to call back, or you want to do a data mining task, or you are doing a search indexing type of an operation where you are focusing on indexing large amounts of data. So in this era of Tera, which I feel this is about terabytes. This is loads of terabytes, loads of terahertz of processing that is going on. Data is always going to be more. In this user-generated content of the in the world where there are 65,000 videos being uploaded in YouTube. There are Facebooks where there are massive data that you have to compute. There are Googles of the world where they have to crunch lots of data. There are Amazons where they are putting lots and lots of products online. When they reach at that particular level, when they are scalable, general computer science principles don't work. We have to reinvent every single point of time to actually do all the scalability metric. And these are some of the principles that I will share with you today. But when we start with the use case, think about any application that's taking a lot of time to process. This is just an example of some of the use cases that we can think. You can think in banking. You can think about financial services industry. You can think any of the back office work or the back office production systems, which are not the website or the web application, but basically focusing on high throughput, massively distributed tasks that we can. Sorry, not massively distributed, long running process. These are some of the examples of a use case. When you think about that in your company, and take that as an example, and then think about the architecture. How are you building that whole architecture? How are you scaling that architecture? How are you meeting the demands of that architecture? In that's where the concept of cloud architecture comes in. Cloud architectures are basically service-oriented architectures that are built on-demand infrastructure. These are architectures that basically come online when you need it, run the complete processing of the jobs jobs that you have to do, and then terminate them. They're terminated when the job is completed. So in effect, they magically reappear reappear when on a trigger of a user request. They scale elastically on demand and then terminate when the job is completed. So that is a concept where we feel the building service-oriented architectures on these on-demand utility-style computing services will effectively give rise to a new set of will solve a lot of different problems. So for example, what it means, basically the job execution time is exactly the same as the infrastructure runtime. So your infrastructure is up only during the job running time. So for example, think of things like websites that are or say for example back office work, say doing payroll. Payroll is something that you can run for 2 hours and then complete all the processing. Or say you are running indexing services that you have to run a particular application, crunch lots of data and do analysis and then produce the results back to your boss. There are in this land where there are lots of data, we have to be really real time in our execution. So for example, in order to stay competitive, I have to kind of crunch all my data on that are available on the Friday, and then crunch it in my weekend itself, so that in my Monday morning meeting I'm able to actually impress my boss with my latest analysis of my updated results, updated data from Friday. So those types of things where you have to do lots of computation, these are infrastructure that will run only during that time, only during the job execution process. And they are repetitive. So every Sunday night or every 2 hours in a day, they are repetitive in nature. They will come online magically. They will do their jobs, and then terminate effectively. So you only pay for the infrastructure that you are actually using, and then it will and scale during that time. So that's one concept. And the second most important concept is thinking distributed or thinking parallel. So think of any task that takes, say there is a job that runs on one particular machine for 700 hours. What if we can take that same job and run it across 700 machines and just run it for 1 hour? Think about that type of, that thing was very difficult. This is basically parallel computing. This is something which was very difficult before, and now it is very easy because there are frameworks that are available to do these jobs easily, and there are applications, platforms that are available that will scale more effectively. So thinking parallel, thinking distributed, thinking massively distributed tasks across multiple nodes at the same time, and then scaling back down when you are done with it. So these are some of the things which will make us more competitive over a period of time. So when you process your job in 1 hour for that 700 machines at a single point of time, now you will be able to produce your results much more faster than your competitor. So that's where you shrink your processing time by adding more CPUs or adding more machines when you need it, and you actually are not investing in that heavy infrastructure. You are actually just renting out somebody else's infrastructure, so you have more control over what you are basically doing. So in parallel computing was very difficult in the past, but just because there are job scheduling was very difficult between the multiple nodes that are running. Now it was very expensive because we don't have that much infrastructure, and it was difficult to coordinate jobs between distributed nodes. So this is where the Hadoop will come into picture. This is where how Amazon Web Services will come into picture, and how I'll share one architecture with you that will show the complete use case of how we can take this massively distributed task across multiple nodes and then complete a particular process. Any questions about this? Okay. So I will share one of the really cool stories. This is a New York Times. One of their chief architects is a fan of Amazon Web Services, and he had a job to do, which was basically converting TIFF images, which are articles from around 11 million articles from the year 1850 to 1922. These are articles that are published so long back, and we want to digitize those articles, as well as kind of convert that data into so that it is searchable into PDFs. So the TIFFs images had to convert it into PDFs by doing OCR and other things. There were 4 terabytes of data that he had to convert. And he had basically no infrastructure to convert that 4 terabytes, a lot of data. So he went to the management to get a sign off for the infrastructure, and he was turned down. So one night, he basically took that 4 terabytes of data, tried to upload in a distributed fashion to Amazon S3, and he converted those 4 terabytes of data into 1.5 terabytes of finished PDFs in a matter of a day by actually spawning 100 instances for 24 hours and crunching all that data into into finished PDFs, and that service is now online. This is just yesterday he put a website interface on the top of that data that he crunched in November. So if you Google for Times Machine and the blog post that is that today that yesterday he blogged about, he talks about how he did the whole thing, how he would never have even started the project in the first place if this was not possible, because getting that much infrastructure in the first place was not possible. When we come to in the case of signing off from management and distributed processing and stuff. So this is a really cool blog post. It talks about what components he used, what open source products he used, and how he went about building this architecture. So please do look at it. So these are some of the stories that we have been we are hearing over and over, and that is what give an idea to the whole concept of cloud architectures. There are certain principles of this cloud architecture, and I will cover those principles when I actually do the example of one of the architecture. So what is that example? Now think of your example in your job, in your business, and then relate it with the example that I will be sharing with you, so that you understand the relations and you understand the scalability itself. This is just an example of one cloud architecture. There can be different ways of building architectures, and this is just the way by which we thought of building it. The functionality of the application is really cool, but the way we have built it is even more cooler. So I will share some of the application details with you. It's called grep the web. How many people know grep? Okay, cool. So grepping is a very simple utility that we use almost on every basis. We thought of an idea that why not we can grep the entire web, and so basically run a regular expression across millions of documents online, so that anybody can search any kind of patterns online and then come back with results. Now, regular expression is a very compute-intensive process, and web is ever growing. So there are always going to be millions and millions of terabytes of data that we have to compute. We have to run that regular expression against and do the processing. So that's what the whole application is all about. It's basically you run a regular expression across millions of documents that have been indexed by one of our subsidiaries owned by Amazon.com called Alexa, and it comes back with the results that are basically results that match that particular regular expression. So what is the functionality here? Functionality is like you can search anything. Regular search engines cannot do certain things like searching source code or searching punctuation marks or searching functions or equations or patterns such as in parentheses disintegration of life, or say just searching email address itself inside say a pattern of email addresses, say all email addresses from Amazon.com. So those types of applications, those types of features were basically the motivating factor for building this grep the web service. I really like the name because it is just grepping the web. And this I termed it as a cloud architecture, and you will see why I share it. So now what I'm going to do is I'm going to zoom in Google Maps style into the infrastructure, into the architecture, one level after another, so that you see the different components together. And once you see the different components, you will see the different ways we have built the architecture so that it is not only just loosely coupled, but it is scalable, it is highly available. What if the hardware itself failed, is resilient in nature. Now those types of things that are important in building a highly scalable architecture. So the first zoom level is basically it takes in a regular expression, it's input output, takes in a regular expression, it takes in an input of data set, which is the crawled index of the web itself, and it comes out with with a subset of documents that match that regular expression. As simple as that, very simple. And because the whole system is asynchronous, we have the way by which we want to get statuses, and so we query the get status to understand how much time does it, what's the status of a particular job. So these are the interfaces of the whole architecture. So if we zoom in a little bit more, this is a zoom level 2. I'm sure are you guys able to see at the back? Okay, yeah. So basically, this is the architecture. So on a start of a regular expression, now we are using these scalable ingredients inside this architecture. We're using some of the infrastructure components and completely the mutually exclusive components inside the architecture. It's not important to use any of these components, but the idea behind cloud architectures is to be service oriented in nature. Point number 1, and to use these on-demand relinquishment and requisition of infrastructure components. So on a start of a regular expression, something gets queued. And a controller, a simple Java controller, is managing the different phases of that process. Launching the instances in the first place, or calling other functions, storing statuses in the database so that I can query and get the statuses, and getting the documents itself. So what is happening in this regular expression, in this whole grep the web project, is on a trigger of a regular expression, on a trigger of a user query, something will get queued. I'll talk about that in 2 minutes. A job gets queued. This job will trigger multiple Amazon machine images and instantiate those machine images into the cloud. It will run Hadoop processing system on the top of this cluster on demand. It will take every regular expression will be matched against our regular expression will be matched against every single document that is part of the input data set. It will compute the data set, it will run the matching algorithm, just a general pattern, and it will aggregate all the results at the back and output all the results. So let's go a little bit details into each of the component. So SQS is used as a distributed transient buffer. It's basically, when I build these scalable architectures, there are very, very important lessons that I have learned. The first and the most important lesson that I've learned is the key to build highly scalable applications or highly scalable architectures is to make it loosely coupled. By making it loosely coupled, if there are two components in the architecture, we want to make it loosely coupled because we don't want to have them dependent on each other. If they are dependent on each other, one component is bombarded with other requests, the other component will also be affected. So we want to kind of keep it loosely coupled so that there is a buffer in between, and that's where SQS will come into picture. It's a buffer in between, so first component will keep on buffering the request, and the second component will be okay if the requests are not coming in. Second most important thing about SQS or the queuing system is the fact that you can have a complete unified interface. All the controller which is I'm talking about in the middle of which is the heart of the system, controller is making sure that I have to get something from the queue, process something, and then put something in another queue. And that itself make the whole process more and more resilient to changes. So never, because the Amazon SQS has been built in a way that is, it's distributed in nature in the sense that there are multiple data centers involved in a particular message. Your message will never be lost if the entire data center will go down to. So because the whole process of distributed and scalable architecture that SQS has been built on. Access control, message locking, all those things are very, very important. When you kind of have a message in between, when you shove a message, you want to make sure that what if the other controller didn't actually process that message? What if the whole machine died? What will happen in that case? So the message locking and message visibility will help address this concern that if the controller failed or if something failed in the whole process, I'm going to make sure that my messages are always processed. So it will again reappear in the queue after a certain message is not processed under a single time limit. So Amazon S3 here is used as a distributed data store for the input data set. So all the documents that are previously crawled are crawled and kept in Amazon S3 because it is it can take massive amounts of data. It is paying by the gigabyte, so we know that we are not charging, we are not paying so much high when the database, the whole web crawler can be going in terabytes of data. So you want to make sure that our costs are low. The third component is EC2, which is very, very important. Question?
Just wondering, since you are using Hadoop for processing,
Mm-hmm.
any reason you're not using HDFS instead of?
I will talk about HDFS as I go into the next level of Zoom. That answer will be given. So basically, EC2 here is basically used as a computing environment. Every single EC2 node is running a Hadoop slave node. So master-slave combination. Hadoop works. I talk about how Hadoop works and talk about how MapReduce work in the next levels of Zooms. But basically, this is every server, because the machines are getting spawned on a server instances, on a web service calls, a trigger of a regular expression spawned multiple instances. And based on the input data set, or based on the complexity of the query, I can decide how many more machines I want to actually instantiate. So say if the input data set is 10 gigabytes and the complexity of the regular expression is say medium, then I want to just spawn say 10 instances. But if say the complexity is very high and the input data set is in terabytes of data, I want to spawn 200 instances because I want to shrink my processing time. I want to parallelly distribute the whole process and then shrink my processing time. So that reservation logic can be built inside your application, so software can actually manage how much hardware it actually needs. So that's the beauty of this whole architecture. The beauty of cloud architectures is the fact that it is coming online when you need it and terminating when you don't need it, and it is scaling elastically during the runtime, during the processing time. So the two basic high advantages of architectures above other traditional architectures. SimpleDB is the database in the cloud. So we want to query as the processes, as more and more users will start using the system and hitting the system hard. I want to make sure that every single user their status is logged correctly, and that needs to be queryable. Queryable in nature. So I need to kind of have in a way, I want to query the data set and come back with the results whenever I want to have about that particular user. So I'm using a distributed, Amazon SimpleDB is a distributed data store which is queryable, and you send in a query on a semi-structured data, and you simply get the statuses of that query. So now I'm going to zoom in a little bit more. And I'm going to share the entire workflow with you about this third level Zoom, where how we are using the queuing and how we are using the controllers, how we are instantiating the instances itself. So let me actually use. I have a cool utility that just zooms in. So on the start of a query, something gets launched on a launch queue. So we have 4 types of queues, and each queue is determining what the phase of a particular job. So on a start grep, which is a start grep function, it logs a message inside the queue. On the launch of a queue, as soon as the controller is basically keeping on polling the messages, for example, if there is a new message that comes in the queue, it will automatically pick up that message on poll and then start their processing. So all the controllers' main responsibility, they share the same base controller, which is take something from the queue, process it, and put something back in some other queue. So that's the whole architecture that will make the complete process more loosely coupled. So launch controller takes the launch message and instantiate based on the reservation logic or the complexity of the queue of the regular expression and say, okay, I'm going to spawn up 30 more instances, 30 more servers on demand, and I'm going to run the Hadoop process on it so that every process can, master-slave combination can run the entire cluster. As soon as the launch processes will complete, it will also log the statuses of every single message inside a database, which is in this case SimpleDB. So it will put the message inside the monitor queue that, hey, I need to now monitor the process because the process is now going to take probably some seconds or some minutes or some hours. I need to make sure that I need to monitor the whole process. So monitor queue will get the message. As soon as the monitor queue gets the message, monitor controller picks up the new message and make sure that it pings. Make sure that all controllers have already come up online and they're ready to boot up and ready to start the whole process and stuff. And whether they are completing the process. As soon as the process is, so monitor controller will start and ping all the processes, and that's where we use the HDFS. This small database icon is where we use HDFS. So HDFS is a local distributed file system that comes with Hadoop, and it's also distributed in a way that small chunks of files are put in different parts of multiple copies of that small chunks are put in different multiple nodes. So when you actually query that API, say you read or write, it will automatically assimilate that chunk and then give you that actual file that was supposed to be read. So by making it distributed, by making it small chunks, it is more reliable, because if machine fails or if the data is lost, the chunks will automatically recreate magically, again, not magically, but recreate that entire file again. So that's why we use Hadoop in HDFS. We use HDFS to store only the files that we need. So, but the actual files are being queried from S3. So Hadoop is being used by S3 automatically in the way that every single processing node will get files from S3, run a regular expression, and store the results if there was a match. So that way, and the other aspect was the billing service. So the whole idea of this cloud architectures gives this new concept of usage-based costing. So previously, in a web application, say I have a website or web application, you don't know how much time your customer is actually spending on their website. You actually just have this whole thing running always on architecture, and you don't know how much time say a customer one is spending just 2 minutes on that on your application, and the customer two is actually spending 5 hours doing lots of processing and other things. You don't know how much to charge them. In this particular architecture, because it is granulated, you know how much time that customer, how much data bits that customer is actually spending, how much data transfer that customer is doing, how much testing that customer is doing, and based on that you can actually say, no, okay, I'm going to, if this customer has spent say 5 instances, I'm going to charge them for 5 instances. So you can do this usage-based costing for your end customer. Another use case for that is, say you are a testing company and you are, say, outsourcing company, and you are testing something for a company in US, say doing load testing or scalability testing or just functional A/B testing or something. Then you have made this system and you are giving infrastructure to your testing customer. You know how much time that customer will be spending on that rented infrastructure, and then you can build on accordingly based on what they have actually used. So that's just for another sidetrack to the system. In here, what we are doing is, based on the complexity of the query, we are actually charging them certain amounts of cents for that query that they built. So it is, if they are charging 100, say if we are querying say 3 terabytes of data and using an email address, there will be a equivalent query charge that pops up before they can actually execute that query. So that's a entire billing and a business model attached to the whole process. And S3 is basically used as an input and output mechanism. So any questions about this architecture in general? I'm going to talk about the best practices in this in the next session, in the next slide. So these are designing principles of any high scalable infrastructure, high scalable architecture, but they are kind of more related to the cloud. First and foremost is the loosely coupled aspect. Using the scalable ingredients is very important. So you keep your infrastructure components fairly loosely coupled, mutually exclusive to each other. The more loosely coupled your systems are, the better scalable it will be. So if they are not dependent on each other, it will and they always serve. Their main architecture idea should be that if you are designing a component, they should have a service level agreement, they should have a service interface, and your particular team, so the 5-person or 4-person team, should be managing that particular service. So once they manage that service, it's their responsibility to keep it up and running. That's the whole philosophy of how Amazon architectures are built. In a complete, so once in an Amazon product detail page, when say you go to a particular product and you look at iPod as the product detail and you see all the listings and the product images and customer reviews and other things, that particular page is rendering services, is getting data from 130 different services. It's basically every team is responsible to build that complete product, that whole service, and it has to, that whole rendering of that page happens via different services. So that's how I call internally as a service-oriented Amazon, SOA. That's the whole, why we are proud about service architectures itself. So loosely coupled is again very, very important. So let's say I would have designed the components. If you remember the Zoom level 3, if I were to design my components in a way that controller A is calling a method inside controller B. This is a general philosophy of how people would have built this architecture. And controller B would have called to controller C. There's a method inside, the method definition is inside the controller itself. So what will happen in this case is, if one controller is bombarded with one request, with thousands of requests, all the other controllers will be affected. Because say one controller is slower in processing, say launch controller is just taking a lot of time, or say monitor controller is just taking a lot of time, then the whole system will be affected, and any user request that comes in is basically bottlenecked. So in this case, this is tight coupling. So in the loose coupling, you kind of create the queues in between. So you have these buffers that will automatically buffer all your requests. So the controllers will never be affected. Controllers will be only worried about getting a message from the queue, processing it, and putting some message in another queue. So that's what makes the whole system highly available and as well as scalable. Other things which I really believe in is the third aspect, where we should assume that things will fail. Hard disk fail almost all the time. Processing, compute nodes fail all the time. The entire switch will fail. Entire hardware, entire processing, the computer processing will die. The powering will shut off the whole rack itself in a data center. So many things happen almost on a daily basis at Amazon. So we believe that we should assume that failover strategy should always be there in your design consideration. So when you are kind of doing failovers, you should make sure that you design your architecture in a way that is automatically will be resilient to reboots and relaunches. So for example, So in the earlier architecture, say in this one, say for example, these are all the hypothetical situations that could happen. Say the controller instance actually failed. So controller is also running on an Amazon EC2 instance. Say that failed for some reason, hardware failure or something, or say earthquake or disaster, whatever. Then once you reboot that particular instance, it will automatically take or automatically get the required Amazon machine image, and then once that image is booted up, because I have a queue in between, I know what are the messages that are currently in process. It will automatically resync with the messages and resume the current state, the previous state that it had. So that gives the whole processing power, the whole the entire system more resilient to changes. And also, this is where Hadoop comes into really nicely. Hadoop is a distributed processing framework, and it takes that processing model such a way that if one node fails, and it assumes that everything is commodity hardware and things will fail. One node fails, it will automatically reallocate resources on some other node and resume that job. So that is the power of Hadoop, and it just abstracts out all the parallel computing problems that people have with parallel computation. And well, the developers just focus on two main things, map and the reduce. They just implement two interfaces called mapper and reducer, and then Hadoop framework will take care of the entire distributed processing, where there is the job scheduling, the automatic parallelization, aggregating of the results. All those happens within the Hadoop framework, so they don't have to worry about it. So last and most important is the thinking parallel. Now processing power has been limited now. You will see like 3 gigahertz, 4 gigahertz. Now that's the maximum processing power that a processor could have. We are seeing a slight dump in the Moore's law itself about processing that they will not continue to do. Now it's important that when the data is so high, when the processing needs no high, we need multi-core. We need multi-nodes. So those are the things that are probably going to be next generation. So you need to think about not only multi-threaded, but also multi-distributed and parallel processing. So zooming in, now I'm going to basically zoom into this part of architecture where I'm going to zoom how I'm just the Hadoop part. So just this part. And I'm going to show you how Hadoop basically works. So this is zoom level 4 inside the architecture. What happens in Hadoop is basically, as I said, there are two main interfaces that a developer who's using Hadoop has to implement. One is the mapper, other is the reducer. So a map function is possible to, it takes that particular job, it distributes across, it breaks it into chunks of the jobs into tasks. That's why a job is distributed into multiple tasks. Each task is a map. So it's a mapper. It basically takes that map and puts it on one of the nodes to process. And it runs that everything in parallel. And once that parallel processing has been done, it will take that reduce process and then combine all the results, aggregate all the results, and then come back with a job. And the results itself will be logged in a database or something, so you can get. So this is a basic representation of the three phases what Hadoop MapReduce does. It just takes a map, it combines the results, and you can run a second reduce phase. To give you an example of how MapReduce works, let me actually give you a real world example of word count. So let's say there are lots and lots of files, like terabytes of data, and you have to do a word count on those tasks. So think about, I want to search developer in the entire text of all the documents on the web or something like that. I want to do a word count on that. So what will mapper do? So the developer has to just implement these two interfaces. The mapper will basically take the input record, and then there are a set of key value pairs that they have to worry about, and then process that and then extract the certain other key value pairs. So in this case, say the text line line on that particular file. There are thousands of files. Now, line on that file is hi Hadoop, by Hadoop. It will basically take this key value pair, take this input record and extract certain key value pairs. It will say hi is 1, by is 1, Hadoop is 1, Hadoop, and these are basically the input to the reducer and output of the mapper. The Hadoop process will take that and combine that results, aggregate that results, and then complete that process in the reducer. So this is the second interface that the developer has to implement. For each extracted key value pair, it will basically combine the values and then share the same key. That share the same particular key. So this is the key and this is the value. So it basically takes that process across all the nodes of all the processing that has been done and does Hadoop 1 plus 1 is equal to 2. So it will automatically do multiple levels of reduces and come up with the actual task. So what is happening here, because the whole mapper is distributed in running in parallel, I am able to shrink my processing time. So in grep the web, question?
Then map is used to represent kind of data structure for representing the task. Is it not limited? So should not use a more comprehensive data structure or maybe something?
Map is not a data structure.
I'm saying is conceptually map is basically key value.
It's taking the key value, taking the input record and then extracting the key value pairs that I am interested in. So that's a good observation. So not all the processes in the world can be parallelizable. Like for example, if your task is say one of the task is input of the second task is dependent on the output of the first task, then that is not parallel. It's not possible to parallelize. Yeah, it is difficult to do the map, but so all the processes cannot be Hadoopized, I would say. But yes, there are lots of processes that can be Hadoop, like those that are repetitive in nature. Think about any job in your company that might be taking a lot of time. It might be a possibility that you might be able, if it is repetitive in nature, you might be able to distribute it and make it parallel. Yes, all the jobs are not mappable. So in the case of grep the web, it was fairly easy for us, basically because our repetitive process was there are multiple web documents to run that regular expression. So we just took that regular expression and every map's one function is to take the file from Amazon S3, which is the input document, run that regular expression, and then give the job to the reducer. So the line number in the document and the S3 pointer, so every object in S3 is having a URL. So it fetches the file, actually does it in multi-threaded to do the whole processing even more faster. But the line number is basically the index number and the document, the URL itself of from the S3. And then if there was a match of that regular expression, it will basically log as another key value pair where there was a true or a false or a pattern inside a regular expression. In the case of reducer, we really didn't need any reducer because we just wanted to take the identity function, which is just a pass through. So it will take the S3 pointer and just gets me all the results back on in a process. So what is happening is all the documents are processed in a parallel fashion. Every document will get the document from S3. Every mapper will get the document on every node, which is running on a Hadoop slave, and then gets the process and runs it and aggregates the results at the end. So that's why the whole the way we created the architecture was we were able to instantiate the whole process by making on a trigger of a regular expression. On a trigger of a regular expression, I was able to instantiate lots of instances. No human intervention anywhere. It's just basically all the logic of how many more hardware, how many more nodes I will need is implemented in a configuration file, and then based on that I will scale. So cloud computing, I think is inevitable. We have seen things like utility computing coming, and in general the way in which it will, the benefits that it comes with, the paying as you go, not having to have the infrastructure, upfront investment, capital expenditure, those business benefits, and also the technical benefits of getting as many that much machines in the first place. Like New York Times would have not started the project if they were not able to get the 100 instances if they for one particular day. And then when the job is done, it's also important to get rid of the machines that you have requisitioned, that you have ordered. You can get as much machines you want, but it's very difficult to get rid of those machines when the job is done. So processing frameworks like Hadoop are giving an ordinary developer, any developer, to do some pretty extraordinary things. Do check it out. There are like lots and lots of use cases that people are building with Hadoop, like financial Monte Carlo simulations on that, and running Wall Street like data analysis on it, data mining task on it, and the variety of different use cases are being used by Hadoop. Open source framework on this, so Hadoop takes care of all the software level headache that is required from parallelization and other aspects, while EC2 and S3 are basically providing the infrastructure that will allow you to put the machines in the place. So now on Hadoop on EC2 is kind of, I feel, is a perfect marriage, because it is creating, giving every developer to do some really good, pretty extraordinary things. So in this new era of Terra, start thinking about parallelism, parallel, multi-threaded, multi-node, because I think that's what I think it's a great future ahead. So any questions that you have? There are lots of pointers. AWS at amazon.com/s3ec2/sdb. Will just sign up and create an account, start up with the process, and I have a blog that I maintain. There are resources, there are forums to answer your questions, and there is also paid support, which is, if you think you need a premium support for your mission critical applications, you can take the premium support plan. So, and my email address is evangelist@amazon.com. And I'm open to taking any questions. Thank you very much for listening, actually. Question? Yeah.
How much of overhead is there while we incorporate this redundancy into the networks, right? For instance, right now I was streaming this, your presentation over the web, and I am just seeing it, right? I see a delay, for instance, just with respect to S3, I am seeing a delay of a minute with respect to overwriting a file and seeing a new file. So I'm sure when you run a framework like Hadoop, you see persistent, going back and forth with the new data.
That's a great question. Yeah.
So how much of overhead do you think practically that exists when you do this?
So we usually, we don't have any data centers in India yet. So we have data centers for S3. So S3 data centers are located in US and Europe. So there will be a slight latency, milliseconds latency when you are accessing from India, if the question was related to India stuff. So what we have done is what people have done, like there are some companies like Pramati and Wipro are building really cool applications on the top of these frameworks. So they have done some benchmarks, and based on that they have had variety of technical as well as different levels of optimizations that they have done. For example, in this particular grab the web use case, what we did was, because the pipe is pretty large, the latency is high, but I can multi-thread that whole request. So each file is not getting, each map is not just getting one file. It is getting multiple files from S3 in the background, and then running the processing on that multi-threaded fashion. So we run lots of threads on each mapper itself. So by doing multi-threaded, even in case of SimpleDB, I ran multi-threaded put requests from an EC2 node to store lots of EC2 data, lots of S3 SimpleDB data, and it will in a multi-threaded fashion. So it will do all the puts. Around 250 megabyte of raw XML data was basically put in a multi-threaded fashion in a put attributes. Because these service endpoints are all can take lots of transactions per second. We are encouraging people to kind of do multi-threaded in this fashion to reduce the whole latency. But yes, there will be latency because this is all hosted infrastructure. These are all, they go to multiple hops before it reaches EC2, before it reaches. Those are the pros and cons about cloud computing.
Okay, just a second question. What is the reason why the input data transfer costs are still not going to zero? I mean, you're still charging $0.1 per gigabyte kind of stuff for the transfer to S3.
I'm sorry, I didn't get the question.
The data transfer charges for going into S3 is still it's still quite high, right? I mean, it's like 0.1.
So upload you mean or download?
Upload.
Upload.
So download I can understand because it's quite low. I mean, you can expect a lot of.
We are finding new patterns of these applications, and as we find more and more such applications, we will be able to do economies of scale and bring the overall cost down. For example, just a few weeks ago, we reduced the pricing for S3 by I think 25% on every data transfer node. So what happens is people like SmugMug are storing massive amounts of data, 20 terabytes a week, and they're gaining growing really fast. So we need to by understanding their patterns of usages, we are putting these layers of tiers on the data transfer. So for example, if you have 10 terabytes data transfer, your charge for that gigabyte upload and download will be like 17 cents, and then it's 16, and then it's 13, and then it's 10 cents a gigabyte per month. So that way, by adding more usages, we are bringing as you add more stuff, your cost will actually go down. But yes, because that's the beauty about cloud computing is that we have the capacity to do economies of scale and bring the overall cost really down. When you compare it with your existing data center or your existing data center that you are building up and you are powering and cooling and maintaining it, then you will see the difference of cost in that way.
Jinesh.
Okay. Question.
Yeah, I'm actually thinking about the cloud itself. I mean, the cloud itself is a series of machines that are actually physically out there, right? That are being shared, probably being shared by a number of different people, or do I get my own instance of that each time? So
if your question is with regards to EC2 specifically, it's virtualized. So it's completely what we call in a virtualization environment, it is very different from like a shared Tomcat hosting environment. It's totally two different environments. Virtualization is based on, we are based on Zen, which is para-virtualization technology, which what we do is we hardware schedule the whole thing. So your CPU, your RAM, your hard drive of that instance is dedicated to that box, to you when you make an instance, because it's virtualized in the nature and it is firewalled between
right, but it's still just partitioning on one machine, right?
Partitioning on one machine, but you will not be like, for example, somebody who is on the same machine, same box will not be sucking up your CPU.
Right, but
because it is virtualized.
But if the box goes down, everybody's going to be affected. Let's say I have a spurious application or something that's running on the box. How is that?
So yes, so that's why we introduce these things, like if there is the case, then these are fairly high throughput boxes anyways, but if we tell them to distribute the whole process, we tell them to put data or your compute in multiple availability zones. So we have the concept of availability zones that by which you can say, okay, I want my 5 instances in this one, and my web application should be also in the second availability zone. Availability zones are logical partitions.
My question is more, how do you stop one application from affecting another application?
So from virtualization environment, your application will not be affected on the other side. So because of the hardware scheduling. So if you Google hardware scheduling on para virtualization, you will know what information I'm talking about.
Okay.
It's a complete slice of that box. In a S3 environment, for example, it's not virtualized. It's a distributed data store. So your data is just lying across multiple instances, multiple distributed nodes. So.
Okay, just one more part to my question. So how quickly are we then going to get into a stage like, so for example, if I take an airline today, right? I mean, the airlines expanded, demand expanded,
Airlines?
Yeah, I mean,
okay.
So for example, I want to go from Bangalore to Delhi today and now, but I can't get it, I'm waitlisted because there's no space out there. So are we going to get into a similar kind of scenario? If so, how quickly are we going to get there?
You mean resource?
Yeah, so I need it now, but then...
Means capacity constraint?
Yeah, capacity constraints.
Yeah, so that is something very high on our list, which is basically, this is something that we do almost on a repetitive fashion. We add capacity almost on the periodic levels. So the time in which we add the hardware is much more less. We have automated that whole process in a way that the time of requisition and deployment and installation is quite less than others. That's the core competency, and that's the secret sauce of what cloud computing is. But so think of this in a way that now, just like Harry Potter books, now we sell Harry Potter books on Amazon, which are we don't know how much it will be getting sold. So we have this prediction algorithms that will tell us how much more capacity people have used from the previous year. And we have the statistics that we share that will tell us how much more we have to stay ahead of the curve, ahead of the usage, so that we are never capacity constrained. So those are some of the techniques that we add. Question?
So Amazon EC2, the virtualization, is it a desktop virtualization or is it an enterprise virtualization? What I mean is...
Desktop, no, it's not a desktop virtualization. It's basically para-virtualization on a grid of machines.
Okay. So you said, you talked about dynamic instances of servers. As on demand, the servers will get instantiated, right?
Correct.
So again, is that dynamic, or do you really allocate a certain number of nodes for a particular user? Or
So now if you go online and right now if you go awsamazon.com/EC2, click the button, sign up for a service, you will get around a 20 instance limit. So we are currently have a cap on that, so that there are no malicious users who are just spawning up instances and going away. Basically what we do, if you want more instances, either you email us or you fill up a form online. In a matter of days, we will basically, in matter of few hours actually, we'll allocate more, we'll turn that switch off so that you can allocate more more instances. For example, animoto.com, I shared that example in my last session. They scaled from 50 servers to 3,500 servers in a matter of 3 days, which is an amazing way. They would have not scaled if they would have not had that hardware before.
So is it truly dynamic? For example, there's a cap on 20 and I'm currently using one machine, one node. So do I need to request for more if I need to use more, or is it like it'll go up to 20?
We just